Alright, this is the last topic for this second part 2 of test 3. It's called Lagrange multipliers, and there's some basic information here that you might want to note. This little history about Lagrange, Joseph Lagrange, and he was 19 when he did this book that talked about this Lagrange multiplier idea. And basically, Lagrange multipliers can be done in lieu of the optimization questions that you did back in Calc 1, which I'm actually teaching and testing on in Calc 1 here very shortly. So here's some actual questions that my wife had put together here, or comments in regards to what you're having to do for all of this. Now, what we want to do is talk about an example to try to illustrate what's going on here. Here's my wife's picture in terms of we want to find the rectangle of maximum area that can be inscribed in that ellipse, and the ellipse equation is given by that equation right there. So I want to go to the next picture for a second here and kind of give you some background for a second. The idea then for Lagrange multiplier is that if you find the gradient of let's do the appropriate color here, if you find the gradient of that equation, which is the hyperbola that comes from the area equation, and the area equation comes from the fact that this is x and x, so that's where the 2x comes from, this is y and this is y, so that's where the 2y comes from, and your area is going to be 4 times x times y, or you have this multivariable function. And in case you've forgotten, if you have some kind of constant, you have 4xy. Let's try that again. You have 4xy. If you solve that for y, you end up with y is equal to some constant divided by 4x. So this equation gives you all of these level curves that you see. And the idea is that the gradient that you have that's going to produce this least amount or greatest amount, depending on which question you're asked, is going to be associated with the gradient that is going in the other direction. Here's the gradient of the ellipse equation. So, according to Lagrange multipliers, then these two gradients are going to be going in the same direction, and they're going to only differ by a scalar. So because these two vectors are in the same direction, they're going to differ by a scalar. And that scalar we're going to use is called lambda. So that's the background of what's happening here. And again, this is the equation of your ellipse if you went ahead and put it in multivariable function form. So again, to reiterate one more time, Lagrange noticed that in order for the condition to be met, the constraint to be met, you're going to end up with two vectors that are going to be in the same direction, and they're only going to differ by a scalar. And so that's what this lambda right here is, the scalar that we're going to be using once we do the process. Now let me go back to her picture and we can talk about the equations one more time. So again, the area is going to be x and another x, that's where the 2x comes from, and then you have the y and the y, that's where the 2y comes from. And this is your multivariable function, which again is going to be hyperbolas that are going to go, these will be different level curves of hyperbolas on either side. That's what this equation would generate, as I said before. The constraint is it cannot be any bigger than the size of that ellipse. And that ellipse right there, if you make it and write it implicitly, you end up with the multivariable function that you saw. So I'm going to pause it now and find the work that we're going to do to actually calculate. Alright, I am back. We're going to start talking about the process of how to do it. Here's the theorem dealing with Lagrange multipliers with one constraint. So what I want to do is bounce ahead to show you that there's a bunch of things that I've taken pictures of as I go through this. I've written the steps on this screen, and so I'm going to go ahead and leave this here for a bit. um, so that you can make sure that you're able to pause it and to stop it. I guess I can highlight a couple things. The process is we're going to need to find the gradients for the f and the g. The f is the thing we're trying to maximize or minimize, and this is the constraint. And I'll show you an example of that in just a second with the parabola, not parabola, but the hyperbola, the area formula that is going to be the largest area we can get inscribed inside that ellipse. So what you have to do is then set this gradient equal to this gradient times a scalar, and this scalar is lambda. So that always reminds me of Revenge of the Nerds and lambda, lambda, lambda. Of course, not all of you are going to remember where that movie is about, but anyway, it's pretty funny. So we are then going to associate the i's, the j's, and the k's if we had that many variables for this thing. We don't. We just have i's and j's because it's a two-variable, multivariable function. So you're going to get an equation for that. You're going to get an equation from that. And then the third thing that's important is your constraint, not written as a multivariable function, but written just as an implicit kind of equation, is going to be the other part of this. And then you have to evaluate this. And now here's where the fun begins. So just a quick story. Basically, when I first started doing this years and years ago, I looked and tried to figure out, okay, what's the different strategies that we have? And I looked at 20 different examples, worked out, and except for a couple minor things like substitution and basic systems of equations, there was some hocus pocus magical mathematics that they use to solve systems of equations. So I can promise you, when I ask you to do one of these, it's either going to be done by some form of substitution, okay, where you're going to solve for one variable in terms of another and then substitute it in and solve, or it's going to be something where you solve for lambda and you're going to substitute lambda in. So you will see that through a couple of different examples, but it can get very convoluted, and if you got nothing better to do with your life, then you can go look at different examples and how they calculate and do the systems. This is crazy. So I'm going to stick with substitution or lambda, solving for lambda and doing substitution. So I'll show you what I'm talking about with this example. So here's the example that we were talking about that I drew the picture before. You're trying to get the biggest area. This is your area formula right here. Okay, and you have this constraint of the ellipse that you have. So we've solved the ellipse for, written it as a multivariable function by just setting it equal to 0, and then whatever that is, after I set it equal to 0, that's my multivariable function. So the next step then for me is to find the gradients. So I think I'd like a different color. So when I find the gradients, that's this part right here. And then I'm going to associate these different parts to get these two equations right here. So 4y is equal to 2/9 x times lambda. 4x is equal to 1/8 y times lambda, and I just went ahead and put the lambda in front. And then I also, don't forget, have the constraint written back in its implicit form. So here's the kind of solving that I was referring to. We do a series of substitutions. I solved it for lambda in equation A. Equation A is this first equation right here. I solved it for lambda, and I substitute this result in place of the lambda in the other equation. I'm talking about equation B right here. After I do that substitution and I simplify it, I cross multiply and I get 16x squared is equal to this 9. This is a 9 right here. Y squared, and then divide by 16 and I get this expression right here. So now I'm going to take this and I'm going to substitute this into the constraint. So I put 9y squared over 16, this right here, in place of the x squared over 9 plus the y squared equals 1. I solve this for y squared and I get y squared is equal to 8. And then I finish this on the other side. Y squared is equal to 8 is the same thing as y equals plus or minus the square root of 8, or if I simplify that, that's like the square root of 4 times the square root of 2, and the square root of 4 is a 2. So I've just cleaned up my radical expression here by factoring perfect square out. Then I go back to my result that I have back in step 1 when I did the equation A. So I'm talking about I went back to this equation right here. Actually it's equation B. And I plug in the square root of 8, and I went ahead and used square root of 8 because, heck, when I square that, that's going to simply be, and I went ahead and did two things in one shot here, so if you want me to write it out, if I could write a 9, we have 9/16 times an 8, and that's how I reduced it to be this 9/2 that you see right here. And then when I solved by taking the square root of both sides, I get x is equal to plus or minus the square root of 9 over 2. And so I get this as my possibilities for x, given this possibility, which was only just the positive version. And it would be the same thing if I did a negative version. So there's actually 4 points. And if you look back at that picture again, if you went ahead and looked real quick, let me backtrack as fast as I can, because I'm doing this on the end of my file. You can see that we have this point, we have this point, this point, and this point. That's why there's 4 points. So too fast, you have the pause button, which you can't do in the classroom. Alright, so that means then our possible answer is this. Well, when we're plugging them into this, to get an area, the area answer is only going to be the positive one because we don't have a negative area. So regardless, if you plug all those numbers in, you're going to get either a positive 24 square units or a negative 24 square units, and we would still just look at the positive version, and that's the maximum length, or maximum area that we would have that's inscribed for that rectangle that's inscribed inside your ellipse. So that's one example, and there's a couple others I want to show you, and I'm going to stop and pause to backtrack. Alright, so here we are starting up again, and it looks like my wife has a variety of steps that you can do for doing this, and it's pretty much the same thing as what I was trying to show you before, but she went ahead and showed it for 3 multivariable functions, and you would just do the same thing. Anyway, this is what she was saying here. It's not easy to solve that system. We're going to stick with substitutions of some form. You've seen one example of that. Now I want to do another example of that. So I'm going to make this go away. So if you want to take a picture of this set of steps or write them down, that's your choice. I guess you don't really want to take a picture of a screen. But anyway, so I'm going to make this move up. And we're going to talk about this example. So we're going to go through the process. And it looks like it's a different kind of shape here. And we want to find the minimum value for this shape, which she's identified as an ellipsoid, based upon this equation, which is a plane. So the plane is going to cut that ellipsoid. So you're trying to find the smallest value for that ellipsoid that is also in the plane. So you found the gradient by taking the, or finding the gradient here. You find a gradient here as well, okay, of your constraint. And that would be the thing equal to 0, and again, the derivative of a constant, it really doesn't matter. You can find this particular gradient pretty easily. Then you associate the 3 different values right here. So you have your 4x, 2 lambda, 2y, negative 3 lambda, 6z, and you have negative 4 lambda. And again, you have your system of equations. This is your constraint right here. Alright, so I want to move this up just a tad. I'm getting better not destroying what I've typed already. And so this time what we're going to do is we're going to take all of these equations that we have, solve them for x, y, and z, and we're going to put them into the constraint and solve it for lambda. So we're using the x, the y, and the z to solve for lambda. And once we solve this, we end up with, after you plug those things in, lambda is equal to a 6. mighty convenient. So you take the 6 and you plug it back into the equations that you have up here, all of these. And so you end up with the point 3, -9, -4. So this point right here is the only value that you have that's going to be associated with that ellipsoid in that particular plane. And this is going to be the minimum value, this 147, after you plug that in to the equation. So this is where the minimum value occurs. So again, that kind of substitution was not too dreadful. Okay, it looks like she actually did that example that we were discussing before. So here's that same example done with her handwriting, if you like her handwriting better than mine. So the process was no different. Here's my equation A, equation B, substituted into the constraint right here, solve for X, and then I went ahead and solved for Y using this other equation back right here. Okay, once I have the Y, or excuse me, I solved for Y, then I put this into the other equation and got the X. And again, you can see when you plug that in, that 24 is going to be the maximum that you have. So if you like this handwriting better, you're welcome to look at that instead of my version I did at the end. All right, keep going. So what we're looking at now is the volume of the largest rectangular box that has faces parallel to the coordinate planes. It's going to be inscribed in that ellipsoid. So it's kind of like what we did with the two-dimensional one, but now we're talking three-dimensional. And so you have a volume that is going to be the product of the 2x plus 2y plus, 2x times 2y times 2z, which gives you 8xyz. And you have your constraint. You find your gradients. And then you write the equations in an appropriate manner where you set the i's together, the j's together, the k's together, and you have your constraint. Be having fun with me writing on this pencil here, getting a couple chuckles. So what are we going to do differently this time? Well, what we're going to do differently is we're going to go ahead and take and add the three equations together that you see right here. We're taking equation A, B, and C, and we're adding those three equations together. This gives us 24xyz is equal to this 2 lambda, and you have 16x squared, 4y squared, 9z squared, which, oh my gosh, happens to be the constraint right there. Okay, so you end up with the fact that you end up with this equation. So I did a little calculating here. So if you take the 144 and substitute it in place of the part that's the same thing as your constraint, we want to solve this for x, y, z. So we're going to do a substitution eventually of x, y, z in place of all these other equations that you see over here, talking about the equations A, B, and C. And so one of the things that we did is we multiplied these equations over here by an x, and we multiplied by a y, and we multiplied by a z to get these new equations that you see down here. So there was an extra step in between that I did not even remotely talk about. So we multiplied this equation A by x, equation B by y, equation C by z. We ended up with this set of equations. After we did the adding of all of those three equations, we ended up with this, and we got that x, y, z is equal to 12 lambda. So now we're going to go back to these equations and substitute in place of the x, y, z's, these x, y, z's right here, we're going to substitute 12 lambda in place of those, get a new set of equations for x, y, and z. So here's the new A. Okay, so you have 8xyz is equal to lambda 32x squared, and eventually you end up with lambda is equal to this version that you see right here, and you can factor that into lambda is equal to 0, and you get x is equal to the square root of 3. Since we're talking about a length, we're just going to not mess with the negative version of that thing. Now, since lambda is equal to 0, let's see then, xyz is not equal to 0, so lambda cannot be equal to 0. We're going to disregard that particular answer right there. And we're going to do something like that again with equation B and equation C. We're going to substitute 12 lambda in place of the xyz, the 8 reduced out with this 8, and so you have 12 lambda is equal to lambda y squared, and you end up with this equation, and you end up with the answers of plus or minus the square root of 12. And again, lambda won't be equal to 0, so we're going to disregard that particular version of the solution to this equation, and the length has to be a positive, so we're going to use that. So as we keep going and we do a similar thing to the new equation C, you end up with this equation, lambda can't be equal to 0, and we end up with z is equal to the 4 plus or minus the square root of 3, and we don't worry about the minus, and so we're just going to end up with that version right there. So if you plug that into the formula, we're talking about the formula that is the original f of x comma y, if I can find it for you. I think I have to go back. Here's the original f of x comma y right here. If you plug that into that formula, you're going to end up with an answer of, went too far, you're going to end up with this answer right here. 64 to the square root of 3 cubic units is going to be the maximum volume that you have to set that or get that rectangular solid inside that ellipsoid. Alright, if you want to do two constraints, let's look at that example. Here's an example of it. I'm going to pause in just a second to give you a chance, if you want to copy it down, to pause the video. It's entirely up to you. I am not going to ask you a question where we do two constraints as part of the test, but let me kind of zoom in and pause so you can see it better. And I'm going to pause for about 3 seconds. Okay, I'm going to move it again. Here's the rest of this for two constraints. And again, I'm going to pause it for a few seconds if you want to copy anything down. Okay, moving on. Actually, here's more of it. Oh, this is another problem with just one constraint. No, it has two constraints. So here's another example of two constraints. So again, I'll pause it to let you look at it, copy it down if you want to. I do not intend to ask you anything with two constraints. Okay, moving on. Here's the rest of that. If you want to copy it down, go to pause. Alright, go to the next page. Let me move it so you can get everything. Go to pause. Alright, then we have to look at the last part of this. And I will pause, so if you want to pause it, you can. Alright, let's see if there's anything left on the other side. Oh my goodness, yes there is. Now you can see why I would never ask you one of these on the test. I will pause. Okay. Alright, here is the last portion of that, and I think that's finally it. Alright, so let's keep going. Now, these are copies of handouts that I have on Canvas that shows examples, and more importantly, what I wanted to just quickly talk about with this is just the substitution process that's going to be involved. This could be something like I could theoretically ask you about on a test. So here's the problem. And again, you have copies of this, so the only thing you don't have is all my beautiful little red handwriting and any kind of description that I add to it right now. So I'm going to kind of zip through the first part of it because it is the same. So we're looking for a point on the sphere. I think I want a different color. And the point on the sphere, here's the equation that is closest to this point right here. So we have to come up with our own distance formula, and here's our distance formula. And I went ahead and took the square root off of that distance formula. So if you're wondering, distance typically is this. If I think about it as a multivariable function and it's equal to 0, when I square the 0, then the radical goes away, and that's where I'm getting this equation right here. Alright, the constraint is going to be this sphere, so we're trying to get the shortest distance to that sphere. So we're going to do the same typical things that we talked about before. I did this organization a little bit differently than I've shown you in the past. Okay, I just went ahead and wrote it as an equation, and then I'm going to associate the i's and the j's and then the k's, and I'm going to get the set of equations that you see right here. And maybe I should use a different color. Alright, so what I did for this set of equations is I went ahead and converted them so that I have them all solved for lambda. That's what I did. I solved them all for lambda. Okay, you didn't want to destroy that in case you want to see that. Then I took the fourth equation and I substituted. Alright, let's see, what did I do? Oh, I didn't go there yet. Did a bunch of stuff over here first. I set equation 1 and 2 from these three equal to each other because they're both equal to lambda. And I ended up with this part that you see right here, where y is equal to 3/2 x. And then I took equations 3 and 1, these two right here, and I solve this and have z is equal to 2x. I'm going to take those two results that we just did right there, and I want to go over to equation 4, this one over here, and I want to substitute those results in place of my y's and my z's. So I'm doing a form of substitution after getting lambda. And let me move that so you can see it better. I plug that in and I end up with just an equation that has x's, and so I get x is equal to plus or minus the square root of 6 over the square root of 29. So it's actually the square root of 36 over 29, and that simplifies to be this. And then I just plugged that into that equation, and I plugged that into this equation, and I got my x and my y and my z. Alright, so when you look at that, then when you figure out what is going to be the maximum distance, it's the negative ones that is going to give you the maximum distance when you plug that into back in the equation for area, and not area, distance. So I'm talking about this equation right here. You plug that in, the negative values are going to give you your maximum, the positive values are going to give you your minimum in that situation for this equation. So I just want you to look at, again, the solving of this, and I've got one more example on the next page, and then I am done with Lagrange multipliers. Okay, and this is probably a great example for you to study, so we'll talk about it again. So we have this function, don't even describe what it is, you might know it as an ellipsoid. We're supposed to find the point in the plane. This is our plane at which this is going to have this function, this multivariable function, this ellipsoid is going to have its least value. So my constraint is the plane, and the ellipsoid is what I'm trying to get the least value for. Alright, so let's just talk through this again. This stuff is, I think, self-explanatory. I'm doing the gradients, and I have lambda times this gradient right here, and I have 4 equations that I'm going to work with. If I take equations 1, 2, and 3, and I solve it for x in terms of lambda, I end up with this set of equations, and I'm going to plug those into this. Wouldn't this be a great question kind of thing for what you have to do? Alright, so I have then, when I plug it in, an equation that's just going to have lambdas. I solve for lambda, and I take this result and I plug it back into those equations, and I get my points, or my point, and this point is going to be the resulting thing that's going to give you your minimum value that's going to occur for that function based upon that constraint being on that plane. So this is, I would say, the easiest one, and I tend to try to ask you questions similar to this when I ask you about Lagrange multipliers. You have to be out of your mind to try to do more than one constraint, or somebody's going to have to pay you big bucks to do that, and you've got a couple examples to go by, or maybe you have a computer program to try to figure out how to do that. Alright, so this is the last topic for your test, and I'm going to stop there. This is part 2 of test 3. So again, this is half a test, and again, the extra, boy, that looks great, part 2 of test 3. Alright, bye.